So we're going to look at the specific idea of integration with substitution. Now we did touch on this earlier, you may or may not recall. But the basic idea is to turn the integral into a standard, some sort of standard integral that we know how to integrate. Now, as I mentioned to you the other day, every assessment task from now on, you will be given a table of standard integrals, and the ones that appear on the standard integrals, we have the basic idea of a polynomial. All right, add 1 to the power over the power. This stuff on the right-hand side, you don't have to worry too much about it. I mean, all it's saying is things like, well, n can't equal -1. Well, clearly, because you'd end up with 0 on the bottom of the fraction there. Also, it means you'd be integrating x to the power of -1, and hopefully you remember that actually that doesn't give you a polynomial when you integrate, that gives you a log function. It says x can't equal 0 if n is less than 0. Well, that's just saying, again, you can't have 0 on the bottom of the fraction. Because if n was less than 0, your index is now a negative, which means x to the power of something would be on the bottom of the fraction, so hence you can't have x's. So, as I say, not something to get hung up about, but they're just technically to make the definition correct. Add 1 to the power over the power. There's the x to the -1, the 1 on x, which becomes a natural log of x. X is greater than 0. That's how the standard integrals gets around the idea of the absolute value of x. Remember, technically, it's the log of the absolute value of x. They're now exponential. Now, the standard integral only has the linear function there. Right? So it's 1 over a out the front, or the coefficient of x. Remember, the way that I like to integrate it is to try and create the derivative times e to the function x. I find that an easier way. Same with the trig functions. They just have the standard there for the linear function, but at least it does help you. Oh, that's right, when I integrate cos, that goes to positive sine, but when I integrate sine, that goes to negative cos. And of course, you can read these backwards. They do become standard differentiation tables as well, because when I differentiate sine, I go to cosine. When I differentiate negative sine, negative cos, I go to positive sine. So again, it tells you when the sign changes. And the third of the trig one is, of course, sec squared. This one we looked at in conics, although we looked at it in terms of differentiating when we were looking at parametrics. And we said when we differentiate sec, we get sec tan. Well, that's the corresponding integral to that. The integral of sec tan is sec. So that's why that one's there. Now we have our inverse tan functions that we recently looked at. So there's our inverse tan one. And for the square root one, it only does the inverse sine. But remember, you could also put minus the inverse cosine for that. They then have a couple of integrals which we haven't looked at yet. It's more for 4-unit integration, and so we shall see this later. The integral 1 over the square root, instead of having a squared minus x squared, they've got x squared minus a squared. And it becomes this wonderful function on the right-hand side, the log of x plus the square root of x squared minus a squared. And there's also one where it becomes a plus under the square root sign, and that one is the log of x plus the square root of x squared plus a squared. Now, you could get asked a question on this. I have seen questions where they've simply said, using the table of standard integrals, go and integrate this. So even though we haven't formally looked at those yet, it would be a very basic one if they did. They might say, go and integrate 1 over the square root of x squared plus 4. Something like that. It's just to say, yes, you know how to use the table of standard integrals. Then we have our non-standard integrals. These are not given to you in the exam, but I would highly recommend that you know them, because it will save you a lot of time. So they're not listed in the standard integrals. There's this one, du on root u. That's 2 root u. So if you see du on the square root of u, or u to the negative 1/2, that becomes 2u to the 1/2, or 2 root u. You might be looking at it thinking, well, why is that so useful? Again, when we start looking at some of the 4-unit integration, you'll see why. That particular situation of du on root u comes up a lot. So 2u root u. And du on u squared comes up a lot too. That's just minus 1 on u. Log x, we don't have a standard integral for log x. It turns out it's x log x minus x. So So another one that I always just find handy to remember rather than having to work it out each time. So integrate log x, you get x log x minus x. Tan x, we don't have that on our standard integral tables. But again, and remember we did do this one when we were looking at the trig ones, it turned out to be the log of sec x, or minus the log of cos x was another way we could have had that one. But this idea, I haven't really talked about it, but when you're talking about trig, if you want to find the integral of a complementary trig ratio, the answer is minus the complement of the answer. So what do I mean by that? If I was to go back to that sec-tan, so if I wanted to integrate cosec cotan, so both of those are now complementary ratios, then it would become minus cosec. So that idea of complementary ratios is always true. If you think about sine and cos, right? Integrate cosine, goes to positive sine. Integrate the complement of cosine, it goes to the negative of the complement of sine. So in other words, sine goes to negative cos. So here's cot. So as I say, cot is the complement of tan. So the answer is minus, and the complement of set is cosec. So we get minus the log of cosec x. And just because I don't like the negative out of the front, I've changed that to the log of sine x. All right, I want to integrate x times the square root of x squared plus 4. Now, I guess we'd put it into index form, x squared plus 4 to the power of a half. Doesn't help me much. We had that useful theorem when it was a linear function inside the parentheses. That's not linear, it's quadratic. This is where substitution can be handy. Mind you, you can also look at it and go, I want to create the situation of derivative. Remember we looked at that when we have derivative function to a power? You might prefer to do it that way, and that's fine. Thing is, in 3 units, they often ask these questions using the substitution, because in 3 units, they always give you the substitution in these situations, which can be unfortunate, because as I say, we look at a question like this, and yes, we go, oh, okay, I just need to create the derivative, and bang, it's very quick. But if they ask the question saying, using the substitution, u equals x squared plus 4, then I have no choice. I've got to use that substitution. In extension 2, they don't generally give you the substitution. It's up to you how you do it. If you want to do it that way, you go. If they don't give me the substitution, then basic idea is this. When substituting u equals function x, the function that's causing the problem, I'll try and make that u. That's the first idea I'll go for. It's x squared plus 4 that is causing the problem, because that's the thing that would be to the power of a half. How do I deal with this x squared plus 4 to the power of a half when I'm integrating? That's what's causing the problem. So if I make u equal 2x plus 4, then we differentiate. So there we go, u. So then I differentiate, because I'm saying, well, okay, everywhere I see 2x and dx linked together, I'm going to replace that with du. So I need to see dx and 2x. Well, if I go back to my original question, I've got an x dx that I haven't dealt with yet. That's easy enough to turn into 2x dx, because I can just multiply that by 2, divide by the half out the front, because effectively I've got a half du there. I've got a half of what I want. So I can change that into a half times the integral of u to the power of a half du. It's now in a standard integral form, x to the power of n. So add 1 to the power over the power, and I get a half, 2/3 u to the 3 on 2, plus of course a constant, and that's a 1/3 u to the 3 on 2. But we don't leave it like that. U is the pronumeral I've introduced. The question was in terms of x, so I need to get it back in terms of x. So substituting back in for u, mere mortals would leave their answer like that. But us super mathematicians will go, 3 on 2, I know what that is. X squared plus 4 root x squared plus 4. And there's our answer. Or. Okay. If you see a root of a sum and of a difference of 2 squares, you could try to turn it into a trig question. Because if you've got the square root of x squared plus 4, if I substitute some trig in for x, I can turn that into a trig identity which will then turn two terms into one term. So if it's x squared plus 4, I'm thinking of my trig identities where I have a trig value squared plus a constant. What's the one I'm thinking of? Yeah, 1 plus tan squared is sec squared. So if I made x equal to 2 tan theta, then that would become, inside the square root sign, 4 tan squared plus 4, which I could change to 4 sec squared. So if they hadn't given me the substitution and I was thinking of one, this is another idea I could try. I notice, oh, I've got a sum of two squares, or it works with difference of two squares as well. If I've got a sum of two squares under there, I might try that. Well, if x is 2 tan theta, dx is equal to 2 sec squared theta to theta. The advantage of this method, you'll notice, is I can substitute straight in for x and dx. I don't have to create anything here. So the x becomes 2 tan theta. The square root of x squared plus 4 becomes 4 tan squared theta plus 4. The dx becomes 2 sec squared theta to theta. Pulling all that together, I'll take the constant out the front, and I have the integral of tan theta sec cubed theta. And you're probably looking at that thinking, well, how has that just made my life any easier? But trust me, once we look at some extension 2 ideas, that actually is a pretty easy integral to go and do. Might not look easy right now because we haven't done a lot of them. I can rewrite this in terms of sine on cos, and it makes it a little bit more obvious now. Because if I change tan to sine on cos, I now have sine theta, sec is the reciprocal of cos, over cos to the power of 4. Sine is the derivative of cosine, or minus the derivative. But I could now do another substitution where I could go, u is cos theta, du would be minus sine theta to theta. This then now becomes minus 8 times the integral of du on u to the power of 4. Well, that's just u to the negative 4. Add 1 to the power over the power. Sub back in for u, and you'll see we've got the same answer. And you're looking at it and going, no, I don't see that. Because the original question was in terms of x, I'm still in terms of theta. So how do I change this back? I need to know what to substitute in. Well, here's my triangle. I know x is equal to 2 tan theta. So I can refer to theta and go tan is x on 2. The hypotenuse becomes the square root of x squared plus 4. So now if I need to substitute in for sec theta, I can read off my triangle. Sec theta would be hypotenuse, the square root of x squared plus 4, over adjacent, which is 2. So it's over 2 cubed, which is 8, cancelled with that 8, and we've ended up with the same answer. Am I saying this is a great way of doing this question? No, I'm not. I'm just saying this is another technique you could use. There are other questions where this idea of, oh, I see the square root of a sum of squares or difference of squares actually is a quick way of doing it. This was not a great question to do it that way. The previous substitution, much better for this question. If they do not say do it by substitution, of course, keep an eye out for that idea which we said before. Can we create derivative times function or that sort of thing? All right, let's have a look at this one. X plus 1 over 4x squared plus 8x minus 7. As I say, in extension 1, they would give us a substitution to use. In extension 2, we would have to think about it. But if I see polynomials, the order of the polynomial on top is 1 less than the order on the bottom, I'm thinking log function. Because derivative over function, differentiate a polynomial, the order goes down by 1. So I see linear on quadratic, probably going to be a log function. Well, if that's the case, if I want to turn this into a standard integral, the standard integral for log is du on u. So I'm going to make the bottom of this fraction u. The derivative then turns out 8x plus 8. Well, that's worked out very nice, because that's just a multiple of the x plus 1 on the top. So I can do this. It becomes 1/8 du on u. And that's just the standard integral for log u. Log u. Okay. Technically, log absolute value of u, but anyway. Sub the u back in, there's our answer. Now this one, dx on x log x all cubed. Okay, what's causing the problem here? Well, the log function cubed is causing the problem. How do I deal with that? So I'll try making that the substitution. If u is log x, du would become dx on x. Oh, hang on a sec. Dx on x. I've got that. So really, this integral is just du on u cubed, or u to the negative 3. And add 1 to the power over the power. Subbing back in for the u, I've got my answer. X over the square root of 1 minus x. Okay, well, no, I don't have polynomial on polynomial, so it's probably not going to be a log function. The square root of 1 minus x, x on the top. It's the square root, I think, that's causing me the problem there. So my initial feeling is to just do u equals 1 minus x, maybe. Could I turn that into a trig identity? Could I go x equals, what would I make it? Sine squared. 1 minus sine squared would become cos squared. Maybe that's an idea. So there's all ideas you can try if they don't tell us. What did I end up doing? Ah, there you go. Look at that one. I did something completely different on that one. I've gone, let's make x equal 1 minus u squared. So in other words, I'm still making u the problem, but instead of what's under the square root sign, I've made it the whole square root sign this time. So I've effectively said u is equal to the square root of 1 minus x. The reason I wrote it as x equals 1 minus u squared is that's easier to differentiate than that. So dx equals minus 2u du. Because, of course, we have restrictions in the domain here, because square root of 1 minus x, bottom of the fraction can't equal 0. We know square roots have to be positive, things like that. So u equals function x as a substitution will pick up those domain problems. Writing it as x equals 1 minus u squared, you don't necessarily see the domain problems now, because you'd think, oh, x equals 1 minus u squared, oh, that's just a parabola. And so you don't necessarily pick up the problems with the domain. 2u squared minus 1 du becomes the answer there, or the integral. Well, that's easy enough. Add 1 to the power over the power. Sub the u back in, square root of 1 minus x. Oh no, mere mortal answer. Look at that. Oh yeah. 1 minus x, root 1 minus x, minus 2 root 1 minus x, plus a constant. All right, let's do a definite integral. Well, hopefully you're looking at this and you're seeing what I see. The first thing I spot when I see that is I've got a derivative times function to the power. So remember, derivative of sine is cos. So if they don't ask me to do the substitution, I know that's just going to be 1/6 sine to the 6, because it's in that form, derivative function x to a power. They're probably going to spoil our party and go, no, 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 use the substitution, u equals sine x. All right, we'll do that. Du is cos x. Problem is, these limits refer to x, not to u. So we need to change the limits as well. But we have a formula for that. U equals sine x. We just use that to change our limits. So pi on 3 becomes the sine of pi on 3, which is root 3 on 2. Pi on 2 becomes the sine of pi on 2, which is 1. And there's our integral. Root 3 on 2 to 1 of u to the 5 du. Add 1 to the power over the power. U to the power of 6. Subbing in, oh, look at that lovely answer. 37 over 384. 37, of course, is a prime number. I think it is. Pretty sure it is. Just thought I'd point that out. Don't they just pop out at you, prime numbers? Okay. X dx on the square root of 25 minus x squared. What am I seeing here? I'm seeing a couple of things here. I'm seeing derivative of 25 minus x squared. So I could rewrite this as derivative times function to some power, bit to the negative a half, but I could do that. I'm seeing underneath the square root sign difference of two squares. So I could do x equals 5 sine theta or something like that. Turn it into a trig equation. I could do that one like I did just before, where I'll make it the whole square root sign and go, well, let's make it u equals the square root of 25 minus x squared and see what happens. Which way did I go? Okay, I've just gone, what's causing the problem? The problem is this 25 minus x squared, the square root of it. So I've just said u is 25 minus x squared for this one. The numbers are going to have to change. So when x is 3, u is 16. And when x is 4, u is 9. Substituting in, we get half u to the minus a half. Add 1 to the power over the half. By the way, there's that u to the minus a half I was talking about. 1 on root u, answers 2 root u. And so sure enough, there you go. 2 times a half is 1. Square root of u you end up with. Root 16 minus root 9 is 1. Oh, you're going to love this one. I always enjoy this integral. Square root of 25 minus x squared dx going from 0 to 5. Now, good. Good. I'm very pleased a lot of people just picked up on that. Because if they don't give me a substitution, then I'm not going to use integration. Because remember what we said? If we've got a formula that we already know to find an area, it's going to be quicker to use that formula than to go and integrate. That is well, actually it's a quarter of a circle, isn't it? I'm only going from 0 to 5. So that would be the quick way of doing it. Unfortunately, they've told us use the substitution x equals 5 sine u. So, going to have to do integration. Dx becomes 5 cos u. I'm just rewriting this in terms of u so I know what to substitute in for u. So u is effectively the inverse sine of x on 5. The limits will have to change. When x is 0, u becomes 0. When x is 5, u is pi on 2. Let's sub in. I get 25 minus 25 sine squared times 5 cos u du. Well, 5 5s are 25 eventually. Oh, there it is. Cos squared. Oh, cos squared. We can integrate cos squared because cos squared we can rewrite as half of 1 plus cos 2u. We can integrate both of those. U plus a half sine 2u. We can now substitute in the pi on 2 and the 0. There's our answer, 25 pi. All right, way we would like to do it. There it is. There's our function. The semicircle. We just want a quarter of our circle there. So quarter pi r squared. Oh, bang. Look how quick that is. Recognize the shape. You save yourself so much time. Don't forget about algebraic manipulation. So what do I mean, don't forget about algebraic manipulation? Integral x cubed, the square root of 4 minus x squared dx. This is possibly a bit too hard for an extension 1 paper, this one. Probably more likely to see it in an extension 2. I can rewrite that, and I'm sure you were thinking the exact same thing. That instead of writing it as x cubed, I could write it as minus x times 4 minus x squared plus 4x. Clearly. Yes. All right? What? Why on earth would you rewrite it? Because look what happens. I can now split it up into 2 functions. X times 4 minus x squared to the 3 on 2, derivative times function to the power of n. 4x times 4 minus x squared to the power of a half, derivative times... I've got something I can integrate. There we go. There's our answer. We just add 1 to the power over the power because it's in that form, derivative. Although I've got to play around with it because I've got minus x there. I really wanted minus 2x, so that's why I've gone a half times there. And this time I had 4x, so 2 times because I only want 2x. If you spot things like that, oh, the markers will be so impressed. Like, this person's a genius. Look at all the time they've saved by noticing that little algebraic manipulation. It's so nice. Let's just look at it. Okay. Whoa! They're all going. Now, let me explain. 6C and 6D is in Cambridge. Not Cambridge, but Cambridge. Okay? So they are the extension 1 exercises where the substitution is probably given to you. Patel, strangely enough, is in Patel. I don't know if the substitution is given in that one because, of course, that's extension 2. But Cambridge, as opposed to Cambridge, is Cambridge. Fake Cambridge. And so exercise 2B there. So again, they're more extension 2 type substitution. Note, remember, substitution. That's not 100% true. I have seen questions in extension 2 where they've said using the substitution, but it's usually when it's a pretty tricky one and maybe the substitution's not obvious.